Uh, Now, in this session, I will discuss about most common physical design questions. Like if you attend as a fresher, these questions are common while interview. Okay, my so this is the first question that every interviewer wants to ask you. Like, what is explain synthesis flow? Okay, you have to physical design engineer must understood like synthesis flow and PNR flow. Okay, you should be like pro in these flows. Okay, first in this flow we have to import all the required files into the tool. Okay, important input files means like .lib file, RTL code. These are the first and important files to start a design to convert RTL code to gate level metrics. Okay. First of all, you have to load .lib files that are timing libraries or liberty files. You can use any word to represent. Okay. Okay. In, yeah, input files you have to load all the input files like as I said .lib files and RTL codes. Okay. I said RTL codes. Okay, there will be multiple RTL codes. Okay, instead of one file, there is no scenario like that. We will have multiple files. You have to load all the files. Okay, for macros you will get some separate RTL codes.
Volume.
Okay, all
Increase
these
your
files you
volume.
have to what
Increase your volume. Volume.
volume. Hello, do you get it now?
Yes. Yes.
Okay. So after loading all the, input files, we have to do elaborate. During elaborate, tool converts all sequential cells like flip flops, not only sequential cells like multiplexers, flip flops, okay, adders. All these codes tool try to understand the logic. Okay, it infers like it will not convert to the gate level. It just understand the code in like these logics. Okay, after that it will create a proper database. Okay, proper database means it will take all the RTL codes and it will arrange like a proper database like this is the first RTL code, then it will take another RTL code and it will take all those RTL codes and it will create one single file, one single RTL code. It will convert into one single RTL code. All these process will be done internally in the tool. Okay. Later, in this elaborate stage also, tool try to remove all unwanted codes in the RTL like assign statements. Okay, if there are any combinational loops in the code, okay, tool it will remove all these all these statements from the RTL code. Then we have to read SDC. What is SDC? SDC is the guidelines for the design, like timing guidelines. It, all our design has to meet this time. Okay, like if they I'm telling like there is a false path in the design. Okay, how tool will know that particular path is a false path? So we have to specify those commands in SDC. These are timing guidelines for the design. Tool uses this SDC and it will it will follow all these timing guidelines to implement a design. Okay, next, sanity checks. What is sanity checks? Sanity checks is the must and should before going to do anything in the PNR or synthesis. We have to do sanity checks. Sanity checks means it is the confirmation that files are properly came to us. Like we have RTL code, we have .lib file, we have SDC. So all these three files are uh, well and goodly written. Okay, RTL code someone written by the designers, but we don't know that RTL code is properly written or not. Okay, there is a SDC, like there is missing in like clock statement. Without clock, we can't do anything in the design. So we have to check all these things. Then if everything is clear in the input files, then we have to go to start converting that RTL code to netlist. Okay, understood? Next, after everything is clean in the input files, we have to, tools will start. Everything can be done by the tool only. Okay, we have to give a proper do file, like proper script we have to give step by step. uh, all these scripts are all some in the companies, maybe they will give. Okay, you can also implement by yourself. Okay, after doing synthesis, sanity checks, generic mapping. What is generic mapping? This stage is very interesting because we have RTL code like undergate, consider one undergate. Someone is writing on the screen. Please don't do that. Okay, we have undergate in the undergate logic in the RTL code. So tool what to in the generic mapping stage means it will take that RTL code and it will represent that code in symbolic level. Do you know symbol of undergate? I will draw. Right. That RTL code. Not only I took undergate as an example. There is like RGate RTL code. Tool converts that RTL code to an RGate symbolic representation, and it will connect these one of the outputs to whatever it has to go to, which get input. It will do that thing also. So here main tool agenda is to convert RTL code to symbolic representation. Only symbolic level only it will have. There is no cell area, there is no power, okay, there is no timing. All these will include after technology mapping. I will tell you what is technology mapping also. So here is only symbolic representation only. Okay, after this uh, technology mapping. What is technology mapping? As I said, we are giving .lib as an input to the tool. So tool takes undergate. Here I took undergate as an example. So tool also, it will take undergate in the .lib file, and it will map this symbolic undergate to that technology whatever .lib file have undergate will map to that undergate. Okay, what will come here, like in .lib file, a foundry will give that .lib file. In that .lib file, there will be particular power, how much it will draw. Okay, how much each input pin and each output pin delays will generate on, or how much capacitance will have that input pin. Okay, and how much delay it will give. All these information will be provided by the foundry through .lib file. So all that information will map to this undergate. Okay. After this technology mapping, tool do optimization. What is optimization? Optimization means like there is a timing violation in the path. for example, there is 100 timing paths are there in our design, but 10 paths are violating setup and hold. Okay, tool what do means it will try to fix those timing violations, or else there is a power target. We have to give some I mean, as per customer requirement, as per customer requirements. They designers will set some power target also. Okay, this design should be uh, uh, consume this much of power only. Like that, they will give some targets. That also we have to. I mean, they will give through SDC only. Okay, those targets also. Okay, and there will be area targets also. Particular design should be fit in 600 into 600 microns, like that. There will be targets. All these targets also will be provided through SDC. Okay, tool will take those targets and try to meet those targets during optimization. All this optimization also can be done in generic stage and technology mapping stage. In generic stage, tool only do this thing, logic restructuring. Okay, logic restructuring means if there are multiple buffers, I mean, there are three buffers continuously is there in the design. So tool will remove those three buffers, because even single buffer do same thing and three buffers will do same thing. Here delay will get added due to each buffer. So tool will remove those three buffers, and it will connect one cell output to another cell input directly instead of going through these buffers. Okay, to logic restructuring means all these included, and it will try to reduce number of logic levels. Okay, between start point and end point. Okay, all these will include, and it will try to remove multi like this one combinational loops. Tool will try to avoid all these things. During optimization also separately it will do. During generic mapping, tool do optimization. In technology mapping also tool do optimization. But separately after mapping all the RTL code to, I mean, converting RTL code to gate level netlist, tool do separately optimization. Okay. As I said, timing, area, and power. These three tool try to meet. After this, DFT implementation. What is DFT? Here, DFT means we have designed some design. I mean, we have created some design. Okay, that went to tape out, means they have manufactured one chip. Okay, how could we know that chip is working properly? Like I have 100 flip flops in the design. Okay, these 100 flip flops working properly or not? How can we check after it is manufactured? So for that, what they will do means they will convert normal flip flops to scannable flip flops. What is scannable flip flops? It will have another two extra inputs like scan input, scan enable. Okay. After chip manufacture, what they do means they will enable that flip flop into, I mean, they will bring from normal operation to scannable operation. During scannable operation, all the flip flops can be connected in the form of shift registers. Okay. Like if in during the testing after manufacture, like I will apply three like triple one. Okay, after applying these triple one, I have to get that three triple ones at output also. Like instead of three ones, there will be generated like 101. That is an issue happened in some flip flop. Okay, that's how they will identify the which flip flop manufactured properly or not. Okay, After this conversion, like normal flip-flops to scannable flip-flops, they will give that database again to the synthesis engineer. This DFT implementation can be done by DFT engineers. Okay, that design again will give back to synthesis engineers. After came back that net list, we have to do another incremental optimization from. During incremental optimization, like in the those scannable flip-flops will generate more delay compared to normal flip-flops. So some timing maybe will affect, and area also will get added because like some extra logics they will small logics like muxes, mostly they will add muxes in the design. Okay, some area will get improve after I mean increase after DFT. So that has to again we have to bring that area, power, and timing to meet our target. After doing this incremental optimization also, we have to generate output files. What are the output files for the synthesis? One is gate level netlist. Another one is SDC. We have given one SDC as an input. That SDC has to generate again. Okay, uh, SDC and I get level netlist SDC and the timing reports. Okay, scan depth. These are the output major outputs of the synthesis flow. Okay, I hope everyone understood this. Next, we'll go to the so this is the PNR flow, guys. UPPD people has to understand every stage properly. Okay, this flow is common at every company, but based on the company, they will rearrange also, but not rearrange. They will add some extra things into the this flow. Okay, but common flow is this one. Wherever you go in the world, everyone follows this flow only. Okay. Please guys don't touch the screen. So here input files. Here also to start PNR flow, we need some input files. What are those input files? Uh, I think you know after synthesis, PNR is the PNR will start. So outputs of synthesis we have to give as an input to the PNR. But here some extra input files also will get added like turbulence. Turbulence .lib file will be included in that turbulence. So I will explain what are the main inputs like gate level netlist, which is synthesized by the synthesizing engineer. Okay, we need that netlist. Next turbulence. Next .left file. Okay, library exchange format. These are the very important files and tech files and SDC. Okay, uh, in synthesis, I haven't mentioned another file like .upf file. UPF file means Unified Power Format. If the design have multiple voltages, okay, then only we need that UPF file. If the design have only like 1 volt or 1.2 volts or 1.8 volts, then we don't need that UPF. But if the design have multiple voltages like 0.8 plus 1 volt, okay, or 0.8, 1 volt or 1.2 volts. If there is multiple voltages in the design, then we need a UPF file. We have to create some domains for those voltages. Okay. I hope these things you people know. So where we are input files, netlist .lib, I mean triple file, left file, stack left, and SDC. And UPF file is the optional. After importing all these files, as I said, sanity checks, we have to do again sanity checks. What is sanity checks? uh, the netlist which was given by the synthesis engineer, it should be clean up errors like errors or combinational loops, multi-driven nets, or like this. It should be clean for every issues. These are very serious issues, guys. The combinational loops, multi-driven nets, and floating inputs. These through floating inputs and multi-driven nets. These are very serious issues in the design. Okay, mostly designers will avoid these kind of issues, but you have to check whether these are have in the design or not. Okay, we have to do all the sanity checks in the library. Here, uh, we should compare netlist and .lib file. All the standard cells present in the netlist should match with the .lib file. Then only we have to move forward. Okay, timing. If there are any missing constraints in the SDC, we have to check that also. If everything is clean, then we have to start floor plan. During floor plan, what we do, creating floor core area. I'm talking all these about block level only. Top level is bit different, but almost same, bit different. Some extra things we have to do. But during floor plan, what we do means creating core area and creating core to IO boundary. We have to create that also. Next, uh, standard cells rows we have to create. Then macro placement, adding blockages. Okay. Next, this thing, uh, pin placement. Okay, all these things has to do during the floor plan. After creating floor plan, uh, next step is power plan, and most of the times people include power plan in the floor plan stage only. Okay, during power plan, what we create means power stripes, power S routes means special routes. Okay, then we have to connect those power stripes and S routes. Okay, from S routes, that power will go to the standard cells. The flow is like this: uh, power pads, then power pads comes to power rings comes to power stripes from power stripes S routes, from S routes to standard cells. Okay, you will see this flow in the top level designs only. In block level, you can see only power stripes and S routes and standard cells. Okay. Sometimes, if, as I said, if the design have multiple voltages, then you may see some these things, power rings for each block. Okay. So most of the times, if the design have only single voltage, then you can see only uh, this power stripes and S routes and standard cells. Then after creating this also, we will move to placement. During placement, there are many stages, many steps are there during placement. Uh, like pre-placement, during pre-placement, we have to add all the physical only cells like uh, end cap cells, well tap cells, and spare cells, spare modules we have to add into the design, which these spare cells can be used at ECO stage. Okay, and next antenna diodes and these TCAP cells. All these cells has to place before going to place standard cells in the core area. Okay, after that placement. During placement, tool follow mainly two things like power driven or placement driven. I mean congestion driven or timing driven. There are three types. Okay, during placement means area it will take as a target. Okay, it will try to improve, I mean use all the available area properly. But during this timing driven placement, tool what do means uh, timing is the major priority. It has to fix all the timing. Okay, it will take timing as a priority and it will place the standard cells in the design. But here during initial placement, what happens means it will or it will not follow any TRCs, like it will try to overlap standard cells or it will not align properly to the standard cell rows. Okay, these things will happen after placing all these standard cells into the design. Legalization will be performed by the tool. During legalization, it will uh, try to avoid all the DRCs, placement DRCs, like if there are standard cells or overlapping, then it will try to move aside and it will try to align to the rows. Okay, all this will happen during legalization. After legalization, scan reordering. I will explain that also later in the slides. Okay, scan chain reordering tool will do. Why scan chain reordering means to make available more. I mean to use properly these uh, uh, tracks, routing tracks, to use more properly use routing tracks. Okay. Uh, I will explain properly in the scan chain slide, scan chain reordering slide. So scan chain reordering. After scan chain reordering, in the placement itself only tool do high fan out net synthesis, like high fan out nets are reset and uh, mainly we see only reset and preset all these pins, asynchronous pins for flip flops. We'll see all these asynchronous pins are the mostly high fan out net synthesis. So tool will buffer. I mean buffering can be done by the tool to those high fan out nets. Okay. After that, like timing optimization and congestion, the tool will try to avoid congestion also during placement itself only. Okay. After all these things done by the tool during the placement, next stage is CTS. CTS is clock tree synthesis. This is the major stage, major time we have to spend on the routing. Okay, CTS is the very critical, not critical, like we have to give more priority for CTS. Okay, because entire design timing will depend only on the clock. Okay, for that we need to take some extra time to do routing for the clock trees. I mean clocks. Okay, we have to build some tree, like each and every flip flop in the design will have to reach the clock from clock port to the flip flop in the at the same time, like without one flip flop getting early clock and one flip flop getting after 1 nanosecond. We have to avoid these things, but we can't do that reaching clock to the flip flops to the zero nanoseconds. Like there will be some difference because one flip flop will placed at the top right of the core area, and another flip flop will be maybe at middle of the core area. So middle of the core area will get early clock if the clock port is at the bottom left of the core area, because it will uh, I mean the distance between the clock port to the standard cell is very less. I mean compared to uh, another flip flop, middle of the core area flip flop will get early, and later the flip flop which was in top right will get the clock. So we during CTS tool will try to avoid these things. Instead of that, tool tool try to do routing to reach clock at the same time to the both flops. Okay, that can be done in the CTS. The CTS is the very we have to spend more time on CTS to learn. Okay, uh, it is like interesting and a bit difficult also bit difficult also. Okay, after doing CTS, we have to fix hold violations majorly. And anyway, we do set up violations at every stage. We have to fix. After clock tree synthesis only, we start fixing hold violations. Okay, because after CTS only, original hold violations will come into picture. Until before CTS, hold violations are we cannot trust. Okay, after CTS only we'll trust the hold violations and we'll start to fix those violations. Okay, after CTS, routing is the stage. So during routing, all the congestion tool will I mean, tool will avoid all the congestion. Congestion means overlapping the metal layers. I mean nets in the same metal layer. Overlapping nets in the same layer. That is congestion. Okay, tool will try to avoid all these shots, and it will maintain proper distance between the nets. And uh, uh, tool converts virtual routes to metal routes. Okay, all this can be done during the routing. And sometimes in real experience people what do means they will try to fix hold violation after routing on. Instead of fixing before routing, they will try to fix after routing, because during routing some nets will get detour. Due to that detour, more delays will get added into the that path. So that's why they will try to fix after routing. The violation is much more than, anyway we have to fix after CTS only. Okay, after routing, sign off stage. Sign off stage means uh, we done all these things like placement, routing, clock tree synthesis. Okay, we have to check whether we are followed all the DRCs. Like DRCs means guidelines that given by the foundry. Okay, to implement a layout. Okay, to implement a layout, foundry will give some information. We have to follow that information.